So now we have the determinant of an operator. So we'll define determinant for operator first, and then go back and define a determinant for a matrix, and then we'll see why these are the same. So the determinant of an operator T on a vector space V is just the product of all the eigenvalues. So it's the product of all the eigenvalues of T, or of the complexification of T, if V is a real operator. Oh, sorry, if V is a real vector space. And these are taken with multiplicity. So that's important. You have to count an eigenvalue once for each time it appears. So if we just look at the distinct eigenvalues, lambda 1 through lambda m, say, and we take the multiplicity of lambda k to be denoted by dk, then the determinant of T is going to look like lambda 1 to the d1 times lambda 2 to the d2, and so forth. Okay, if we take them as undistinct or repeated according to multiplicity, then there's potentially more of them. So I'll have the final subscript as an n instead of an m. So these are repeated according to multiplicity. Then if we look at the characteristic polynomial, and so let's see, so if this is say P of Z is equal to, and it factors as Z minus lambda 1, Z minus lambda 2, all the way up to Z minus lambda n. And I'm assuming that we're working with the complexification if necessary, so that the polynomial splits into a product of linear factors. Then what we get from this, well, we've seen so far that by picking the z from each of these terms, we're going to have a z to the n as our leading term. And then when we look at the z to the n minus 1 term, the coefficient for that guy is going to be found by picking one of the lambdas from one and then z's from all the others. And so that ends up giving us just the trace of t. And that one lambda is going to bring a minus sign, so we end up with minus the trace of t. Oh, I guess I should write it out more fully. I was writing this as trace t before, so I'll continue with that. And then there's a bunch of other terms in between. And then the very last one that we get is the constant term. And the only way that we get a constant out of this is if we choose the lambda from each one. So we're going to get the product of all the lambdas, and each one comes with a minus sign. And so there's n of those. So we have n minus signs. So we have minus 1 to the n, and then the product of all the lambdas. And so then that part is exactly the determinant of t. So the determinant of t is the constant term up to a sign in the characteristic polynomial. So then we have theorem 10.24, which is that an operator is invertible if and only if the determinant is non-zero. And so to prove this, I'll work with the contrapositive of the statement and say, let's look at when t is not invertible. Well, t is not invertible if and only if the null space of t is not just 0, right? So in other words, if it's strictly larger. But the null space of t is the same thing as the eigenspace of 0. And so the eigenspace of 0 contains more than just the 0 vector if and only if lambda k equals 0 is an eigenvalue. So this happens if and only if 0 is an eigenvalue. So maybe that's actually a better way to rewrite what this line is supposed to be saying. 0 is an eigenvalue. That's the meaning of this line. And if 0 is an eigenvalue, one of the lambda k's is equal to 0 if and only if the product of all the lambda k's is equal to 0. Because when you've got a product of numbers equaling 0, that can only happen when one of them is equal to 0. And so that thing that we have in the last line is the determinant. So we are done.